Okay, in last class we were seeing solve the numericals on the concentric tendon, eccentric tendon, okay, of the regular shapes, symmetrical sections, and also one numerical on I sections. Okay, so just for glance, stress at the bottom, which is equals to P upon A plus P into E upon ZV for top fiber, which is equals to P upon A minus P into E upon ZT. Okay, when the load is not given. Okay, so when loading is provided, we have to determine the dead load and live load. Okay, dead load and live load will be already given. So the moment with respect to dead load we have to find out, and moment with respect to live load we have to find out. Okay, so and this is the formula for the respective top and bottom fiber. Okay, so in last class we have solved about the I sections. Okay, so we will see another type of numerical. Here he says that a prestressed concrete beam of section 200 mm wide by 300 mm deep. Okay, the section he has given, that is 200 mm wide and 300 mm deep, is used over an effective span of 6 meters. Okay, the length of the beam is 6 meters to support an imposed load of 4 kilonewton, that is live load he has given, which is equals to 4 kilonewton per meter. Then the density of the concrete he has given. He says that the concentric prestressing force, okay, the concentric prestressing force necessary for zero fiber stress at the soffit. It means that he is saying that FB is equals to 0. Okay, stress at the bottom fiber is 0 when the beam is fully loaded. And second case is that the eccentric prestressing force located at how much? 100 mm. Eccentric he has given, that is E equals to 100 mm, sorry, located 100 mm from the bottom of the beam. Sorry, bottom of the beam means from here to here he has given, that is 100 mm, which means that eccentricity will be equals to 50 mm, because this is 150, from here to here we need, that is E. Okay, bottom of the beam, which would nullify the bottom stress due to the loading. Okay, so before solving the numericals, what you do, just read the question twice. Now the first thing is that we have to draw the figure, that is 200 upon 300. Okay, and one second. Just I'm writing down the given thing. This will be 150 and this will be 150, and he says that and at the second case. Okay, so at the first case it is a concentric means it will be at the center. Okay, first on I will solve the first case. So here A will be equals to how much? 200 by 300. Okay, then here he has given the length and width, and also he has given the live load. Live load, it was 4 kilonewton meter. Okay, and span of the beam was 6 meter. Correct. Therefore find out the and also he has given the density that is 24 kilonewton per meter cube. So first thing is that find out the dead weight. Okay, so dead weight will be equals to how much? 0.2 multiplied by 0.3 multiplied by 24, okay, which will be equals to 1.44 kilonewton meter. Okay. And also directly we have the live load. We have got the dead load and we have got the live load. Now what we have to do? We have to determine the moment due to dead load, mg, that is W L square upon 8. Here W will be dead load, that is 1.44 multiplied by span is 6 divided by 8, which is equals to 6.48 kilonewton per meter. Sorry, kilonewton meter. Similarly, movement due to live load will be equals to WL square upon 8. Live load how much he has given? He has given 4 kilonewton. 4 into 6 square upon 8, which is equals to 18 kilonewton meter. Correct? Therefore, he is asking that the concentrating prestressing force necessary for a zero fiber stress at the soffit when the beam is fully loaded. Therefore, tensile stress at the bottom fiber, okay, which is equals to, and he says that the load will be equals to 0. Therefore, directly what you do, you take these two, sorry, P upon A, okay, the first case, P upon A, that is P is how much? We have to determine that P value. Okay, we don't know the value of P. Therefore, stress will be equals to 0. Sorry. Bottom fiber P upon A plus mg plus mq upon z. Okay, because here he has given the loading, okay, for concentric tendon. If he has not given the loading, means fb will be equals to directly P upon A, but here he has given the loading, so substitute the values. P will be 0. He says that in question he has directly mentioned that for 0 fiber stress at the soffit, okay, therefore it will be 0. P A value it is 200 by 300, okay, this one 6.48 plus 18, okay, right, in terms of Newton. Z value what it will be? BD square upon 6, okay. Therefore, we have to determine the unknown value, that is P. Therefore, after solving, we will get P equals to 489.6 kilonewton. Okay. So this was about the first condition. Now, in second condition, I will read the question. The eccentric pre-stressing force located at 100 mm from the bottom of the beam, which could nullify the bottom fiber stress due to loading. Okay, and again here we have to determine the value of P. P value is not given. Okay, pre-stressing force it is here, and it is located at how much? 100 mm from the socket, which means that eccentricity will be equals to 50 mm. Why? Because it is 150, 150, and this is 200. Okay, and we know the formula that Fb equals to P upon A plus P into E upon Z minus mg plus mq upon zb. Okay, so you know all the values, just directly substitute in the given thing. So this fb will be equals to 0, p upon a. P we have to determine. A value is how much? 200 upon 300. Okay, again p value we have to determine. Eccentricity how much it is? It is 50. Z value is how much? That is, Z will be equals to BD square upon 6. Okay, for rectangular symmetric section. Therefore, B is how much? 200. D is how much? 300 upon 6 minus mg value how much we have got? We have got 6.48 plus 18 divided by again 200 into 300 square upon 6 multiplied by 10 power 6. Why 10 power 6? We have converted this kilonewton meter to Newton per, sorry, Newton mm. Okay. Therefore, the value of P after solving, the value of P will be equals to 244.8 kilo Newton. So from this question, if you are placing your tendon at the center, okay, if you are placing your tendon at the center, then how much load pre-stressing force you have required? You require, that is 489.60 kilonewton of force is required. Suppose if you are placing your tendon at some eccentricity, say 50 mm, load is required to 244.80 kilonewton is required. 1 second, I'm getting call. I'm audible.
Yes, sir.
Okay. So from this question, we'll come to know that if we are doing, if you are placing your tendon at the center, then how much force is required? 489.60 force is required. And if you are placing at a certain eccentricity, say 50 mm, with respect to this cross section, then how much load is required? That is 244.8 kilonewton force is required. So anybody having doubt here? If you have doubt, means comment yes, no. If not, comment n, y or n. Shall I move to the next question?
Yes, sir.
Okay. So here we can see the pre-stressing force at the concentric and at the eccentric. The magnitude of the computed pre-stressing force is clearly indicate that the advantage of eccentric prestressing in the flexible member subjected to the transverse loading. So it is better to provide the prestressing force at the certain eccentricity in with apart from the concentric, because to nullify the tension in the concrete members. Okay, so this one you can solve it the same thing, you can take it as a homework. So next step we will see, that is again symmetric I section. Okay. So the section, first I will draw the section. For these kind of problems, your engineering mechanics should be strong. The top flange width is 250 and the thickness of the flange, top flange is 80 mm. All dimensions are in mm. Okay. The thickness of the web is 80 mm. Bottom flange thickness is 80 mm and width is 250 mm. Okay. Therefore, this is a symmetric I section. Okay. And the given things are like this. Live load, which is 2.5 kilonewton meter. Eccentricity, he has given 100 mm. Span, it is 8 meter. Then overall depth, overall depth 500. Okay. In notes, actually in that notes, in figure it is not mentioned. Okay, 500 mm. Just keep in mind while you are referring that one, the overall depth is 500 mm. Okay. And he has given pre-stressing force of 115 into 10 power 3 Newton. Okay. In textbook also it is there. This question it is available in textbook also. So it, as it is a symmetrical section, directly we can solve the numerical. See, its neutral axis obviously it will fall at the center. Okay, it is symmetric about x-axis and it is also symmetric about the y-axis. This is 250 and this will be 250. Okay, and we have the formula, that is P upon, for top it is P upon A minus P into E upon ZT plus mg plus mq upon ZT. Okay, for bottom fiber it is P upon A plus P into E upon ZB minus mg plus mq upon ZB. Okay, and one more special case here, it is that he says that there is a loss of pre-stress force. 18% of pre-stressing force is being lost. Okay, in next chapter we will see different types of losses. Okay, what you mean by that losses. Okay. So while doing that pre-stressing force or after pre-stressing that one, he says that there is a 18% of loss. Okay, then how much p we have to take? Okay, this p. While solving that one, I will tell you. Okay. Now, first thing is that determine the value of a. First one, a equals to, we have how many sections? One, two, three. Three components are there. So calculate those one. 250 by 80 plus 80 multiplied by this 80, this 80. Total depth is 500. 500 minus 80 minus bottom one, which is equals to 340, and again 250, 80. Okay. On solving this one, the area which is equals to 67200 mm square. Correct. Then we have to determine the value of z. Okay. So you can directly calculate the value of z, that is I upon y, but here we need I value. So I value can be written as BD cube upon 12 minus BD cube upon 12, which is equals to 2. I will explain here only. The same thing. Okay. We'll calculate the value of I. After I, we'll calculate the value of Z. Okay. After Z, you have to calculate the first. We have to calculate the dead load. Okay. After dead load, you have to calculate the movement due to dead loads. Okay. So how will calculate the dead load? That is Wg will be equals to, first take the top flange, that is 0.25 by 0.8. Okay, then we have web. Okay, that is 80 into, sorry, 0.8, 0.08 multiplied by 0.34. Okay, that is the depth of the web, 340. Then we have again bottom flange, 0.25 multiplied by 0.08. Okay, this whole multiplied by density that is 24, you will get the dead load. Okay, say x, y, z, you will get the dead load. Take this load and substitute in the moment equation, that is WL square upon 8. So you will get the moment due to dead load. Therefore you will get the moment due to dead load and moment due to live load. Now we have the formula, that is Ft, one I will take T upon A minus P upon Z plus moment upon Z. Okay. Now here he has mentioned that is a 18% of loss. And here what you have to take, that is 100 minus 80, which is equals to 82. The remaining how much force is there? 82% is there. Out of 100%, 80% has been lost. For how much we are left with? 82%. Therefore, what you have is 2. My value how much it is there? 115 10 power 3 divided by 8 is 67200 minus, again p there, you should not take 100%, we have to take 82% because 16%, 18% loss is there. Multiplied by 115 into 10 power 3 multiplied by eccentricity, how much is there? 100 mm is the eccentricity. Therefore 100 divided by z value we have calculated, that is 8.189. Therefore the procedure is same. Here what I have done, I have calculated the direct stress separate, bending stress separate, moment stresses. Okay, separates are there. Therefore what you do, just write down up to the given things. That is at first condition, pre-stressing force plus self weight. Okay, pre-stressing force plus self weight means the formula will be Ft will be equals to P upon A minus P into E upon Z. Only self weight means you should take mg upon Z. Okay, if we ask self weight and live load means then you have to take mq upon Z. Okay. This the first condition is that pre-stressing force plus self weight. The second condition is that pre-stressing force plus self weight plus live load. Okay, these are the forces. So next one, that is most important for your MCQs also, that is losses in pre-stressing for concrete. 1040. So we have n number of losses. Okay, either in pre-tension, either in post-tension. Most important concept, so listen it very carefully, try to understand it. Pre-tension. Okay, what you know what you mean by pre-tension and what you know what you mean by post-tension. Okay, the name itself indicates the tension is given before the hardening of the concrete is nothing but pre-tension. If the tension is given after the hardening of the concrete is called as the post-tension. Now, what are the losses in pre-tension? First, we will see about the losses in the pre-tension. The first loss is that elastic deformation of the concrete. The second one is relaxation of stress in the steel. The third one is shrinkage of concrete, and the fourth one is creep of the concrete. Okay, and what are the losses in post tension? Okay, here the first case is most important. If okay, all the if there are n number of cables or tendons. Okay, if all the cables or all the tendons are tensioned or pulled or given force, if all the tendons are tensioned simultaneously at a time, then there will be no loss. Okay, if they tension the first one and they tension the second one, third, fourth, five, if they do all, if they go on doing individually means there will be loss due to elastic deformation. Okay, this first loss. Okay, this first loss will be there. If all are tension at a time means then there will be no losses in the post tension. Okay. The second one is again relaxation of strain in steel. The third one is shrinkage of concrete, creep of concrete, friction and anchorage level. Okay. Just remember what are the different types of losses in the pre-tension and post-tension. Okay. Now we have code book for this one, that is IS 1343, and it is not necessary to remember the formulas if the mode of exam is in offline. If it is online means then you have to remember the formulas. In page number 16, some important formulas are there. Better write down the page number, or if else, if you go on solving the numericals means you will come to know. Otherwise, one second. So just now we solved the numerical I section. The entire question is in the available in the reference textbook. Okay, from there you can copy the question. Page number 116. Okay. Before going to only for your exam, he will directly ask the questions. Sorry, numericals instead of theory. So remember this table. Okay, that is pre-stressing force, sorry, pre-tensioning and post-tensioning. So in pre-tension, the elastic deformation will be there, relaxation of steel, shrinkage of concrete, and creep of concrete. And its post-tension, no loss due to elastic deformation. Remember, if all the wires are simultaneously tensioned, means all the wires they have pull, giving tension to that all the wires simultaneous at a time, means then there will be no elastic deformation. If not, then if they are doing individual means then there will be a elastic deformation. If the wires are successively tensioned means one after one, there will be loss of pre-tension due to elastic deformation of concrete. The second one is relaxation of stress in steel, shrinkage of concrete, creep of concrete, friction and anchorage. Okay. So do one thing, uh, take notes and write down the formulas. Okay. So directly we will solve the numericals. So the first one is loss due to elastic deformation. Okay. So the formula will be alpha E equals to ES upon EC. Okay. What is meant by ES? ES is nothing but a modulus of elasticity of the steel, and EC will be equals to modulus of elasticity of concrete, and alpha E is nothing but the modular ratio. Okay. Sometimes in question he will give the formula for the sorry, directly will give the modular ratio, that is alpha E. If not, you have to sometimes you have to assume it. Okay. Therefore, the loss of stress, which is equals to elastic deformation due to the sorry loss due to elastic deformation, is nothing but alpha E into Fc. Okay, what is Fc? Fc is nothing but a pre-stress in the concrete at the level of stress. So if you want, you can take the screenshot. Be quick, or if you want, you can note it down. The loss of pre-stress due to elastic deformation of concrete depends upon on the modular ratio and average stress in the concrete at the level of steel. Therefore, Fc is nothing but the stress in the concrete, Es is nothing but the modular elasticity of steel, Ec is of the concrete, and this formula is most important. Remember, modular ratio is equals to Es upon Ec. You have already learned in this sum. Okay, strength of material. Stress in concrete at the level of steel, it is given by Fc upon Ec. Okay. Stress in this steel corresponding to this strain, it is given by Fc upon Ec into Es. So don't get confused, just remember this formula and this formula. Okay, don't take tension. So take the screenshot. At a time we will solve the numericals. Okay, and whatever the numericals are there, all are from this reference textbook. Okay. Now the next formula, the next loss is that loss due to shrinkage of concrete. Therefore, the loss of stress, it is given by epsilon Cs multiplied by Es. Okay, epsilon Cs, the value will be 300 into 10 power minus 6, and Es value he will be given in the question. Okay, that is modulus elasticity of this steel. Remember this one. Es is not. Okay. What is the page number? 148. Okay. So the one by epsilon Yes, epsilon Cs for post tensioning, it is 200 into 10 power minus 6 log of 10 T plus. Okay, and it is a pre-tensioning, the value will be 100 into 10 power 6. Okay, take the screenshot of this page. चालू है ओ तुरंत फोन किया था हाँ 10 मिनट से okay so if your concrete is a tension then use this formula and if it is the post tension then use this formula. Okay, great. In question, he will mention whether it is a ultimate creep strain or it is a creep coefficient method or by ultimate creep strain method. Okay, the formula is, if he says that use ultimate creep strain method, then the formula will be epsilon cc, fc, and es. Okay, epsilon cc will nothing but the ultimate creep strain of the sustained until stress. Fc will be the compressed stress in the concrete, and es will be the modulus of elasticity. Okay, and if he says by free coefficient method, then the formula will be like this much, only this much. Okay, don't get confused. Loss of stress in steel will be equals to phi into fc into alpha e. Okay, this much, and don't try to substitute all those to this much. Okay, so if you want, you can take the screenshot. Be fast. Creep coefficient. And sometimes you won't give the value of creep coefficient. Just remember the formula, that is epsilon t of epsilon e. The thing is that here you have to remember the formulas. Okay. Once you start solving the numerical, it will be fixed in your mind, and most of the formulas are available in the codebook also. Okay. Don't get tense about the remembering the formulas. Okay, loss due to relaxation of the steel. Okay, sometimes he says that there may be a relaxation of 5%, 10%. Just now we have solved in the previous problem, that is 10%, sorry, 18% losses for there. So like that he will give some relaxation, so we have to deduct from that one. Then loss due to friction. Yeah, it's here. Loss due to friction, that is which is available only in the post tension concrete, not in pre-tension concrete. Okay, so the formula will be P equals to P naught into E raised to mu into alpha plus K into X. Okay, so what is mu, what is alpha, what is K, we will see while solving the numerical. Just remember, mu is nothing but the coefficient of friction, which we already learned. Okay, alpha is nothing but the cumulative angle. Okay, then K will be the friction coefficient for the wave. E is nothing but the exponential, and the values of mu he will directly give in the question. Okay, need not to remember. Then loss due to anchorage slip. Loss due to anchorage slip means this is your beam and the tendon will be going here, such that the tendon should not slip. Then also there will be slippage. Okay, so that one we will calculate by Es into delta upon L. Okay, the loss due to anchorage slip will be Es into delta upon L. Delta is nothing but the slip of anchorage. L is the length of the cable. A is the cross section. E is the modulus elasticity of the steel, and P is the prestressing force. So these are some formulas. Okay. So with respect to these formulas, tomorrow we will possible afternoon we will solve some numeric. Okay. So you can comment your roll numbers and you can leave the class. In next, and don't try to miss the next class, because in next class I will be taking the numericals with respect to the losses. I will give you a glance about it. Okay. Yeah, he is asking for the elastic model, elastic deformation of the concrete. Okay. Sometimes he will ask for the mix, and he will ask for the stresses, okay, with respect to the losses. Okay, in previous problem we have solved in I section. One second. Yeah, here.
See, 18% losses is there. After calculating all the losses, we have to determine the stress at the bottom and stress at the top and the bottom. So first what we have to do, we will see whether it is a pre-tension or post-tension. So what we will do, we will calculate all the losses. Okay. By calculating all the losses, we will get certain percentage, that is 18% also of loss. So with respect to this 18% of loss, we will calculate the stresses. Okay. So there is a connection between one numerical to another numerical, but not that much headache. Okay. These are examples with respect to the shrinkage. Okay. These are with respect to creep, with respect to the frictions, anchorage slips. Okay. Yeah. By the next class, your first unit will be completed. Okay. So comment your roll numbers and you can leave the class. But there is a connectivity with respect to one numerical to another numerical, so don't try to skip the class.